Welcome back, everyone. This is CS 48680, Introduction to Machine Learning, as taught at the University of Waterloo in the fall semester of 2024. And so this is lecture 5, which I've titled Logistic Regression and Numerical Optimization. And so this is going to combine ideas we had from classification and regression and give us a new technique that'll enable us to assign a level of confidence in the prediction of class labels. All right, so before we get into the technical details of logistic regression, let's set the stage with a simple example. So let's imagine a situation where an animal shelter wants to predict whether a cat will be adopted within 30 days. You know, clearly, if the shelter had a way to predict the likelihood of adoption, they could figure out which cats might need more attention, promotional efforts, or special care to increase their chances of finding a home. Yeah, so for example, knowing that older or less playful cats are less likely to be adopted, within a given time window could allow the shelter to strategize, maybe ensuring those cats are highlighted, or planning special outreach efforts. And so this ability to make accurate predictions will go a long way towards helping the shelter manage space and improve the adoption rates, ultimately being able to deliver better care for these little animals. And so, yeah, let's imagine that the shelter's collected a lot of historical data about the cats. So this table depicts the data set. Each cat represents a row about which we have information concerning its age, as well as how playful it is on a score of 1 to 10. And then whether or not it was adopted within 30 days of this information having been collected. So here we can see that this kitten because it's 0.3 years old, somewhat playful, was adopted within 30 days. But this 6-year-old cat that's not so playful was passed over. And so the outcome the shelter really cares about is whether the cat was adopted within the 30-day period or not. And so if we can take a closer look at the cat adoption data set to see how some of the key features relate to the outcome of whether the cat was adopted within 30 days. So on the left-hand side here, I've got 2 scatter plots that help visualize this relationship. So the top plot shows the relationship between the cat's age and whether or not it was adopted within 30 days on the y-axis. So each point represents a cat, and yellow indicates that it was adopted, so adopted equals 1, and not adopted in purple. And so we see a clear pattern here. The younger cats tend to have a higher likelihood of adoption. The successful adoptions are concentrated toward the left, so the younger cats over here. But the purple points are clustered more strongly for the older cats to the right. And then similarly, the second plot examines the relationship between the playfulness score and the adoption within 30 days. So we can see that the playful cats are more likely to be adopted quickly, while cats with a lower playfulness score appear less likely to find a home within this window. And so we can combine this individual information into a combined scatter plot that shows both the age and the playfulness together. So the color of each point here still represents whether a cat was adopted within 30 days, where yellow is adopted and purple is not adopted. And so we can see that younger, more playful cats are predominantly yellow, meaning that they're adopted within 30 days at higher rates. And so in contrast, older, less playful cats cluster in the purple region, indicating lower adoption probabilities. So how can we handle this? Well, we can see that the classes aren't linearly separable, like we encountered with the perceptron. But there is a clear trend. And so as we move from the top left to the bottom right, the chances of us encountering an adopted cat drops to 0. So K-nearest neighbors, because it can handle non-linearly separable classes, it might be overkill. because we don't need to learn a highly irregular decision boundary like k-nearest neighbors can give us. So what can we take as our goal here? So I've been using these words, chances of us running into an adopted cat, likelihood of getting adopted, probability of getting adopted. I've been using those very informally, but that really gets at the fundamental idea of how we want to approach that, how to approach this. We're not really as interested in a clear-cut decision boundary anymore. We want this to be a bit fuzzier. We want this to reflect the probability of running into an adopted cat as we move from the top left to the bottom right. And so why does this matter? Well, in our particular example of making decisions about cat adoption strategies, understanding the probability of an event happening, it's far more useful than just predicting the outcome. So yeah, to get a handle on this, let's consider two different types of predictions. So prediction A, a cat will not get adopted in 30 days. It's a simple yes, no answer, straightforward classification task, just gives us a binary output. But we only have the result, right? We don't have any kind of degree of certainty or likelihood of that result. And as we know, predictions, performance on the test data that we haven't seen yet, they can be wrong sometimes. And in this case, if we're wrong, that can have real world consequences. Prediction B, on the other hand, the probability that a cat will not get adopted within 30 days, the probability that a cat will get adopted within 30 days is 5%. Okay, so this gives us a bit more information. It not only makes a prediction, but it gives us a probability associated with that prediction. Like I say, it's a 5% chance that a particular cat will be adopted within 30 days. It's a lot more informative because it's not just a hard yes or no. Now we've got a continuous output that tells us how likely something is to happen. And so this allows us to prioritize our efforts. So for example, we can focus on cats that have the lowest adoption probabilities. For example, by adjusting adoption fees or maybe launching a targeted marketing campaign. And so this distinction is important because it actually helps with generalization, which is critical for making decisions about future cats that arrive at the shelter. So we trained our model on historical data, but our goal isn't to predict what happened to those cats, because that already happened. Instead, we use that information to predict what is likely to happen for new cats, especially those with similar but not identical profiles to those we've seen before. And so knowing the probability allows us to tip the scales in favor of cats who are least likely to be adopted. And so armed with these probabilities, the idea is that we can make more informed, justified decisions, ensuring that our resources, whether they're marketing efforts, adjusted fees, special events, we want to ensure that those efforts are directed where they're going to have the most impact. Okay, so one way to formalize this problem is through logistic regression. And so today we're going to focus on exactly what that is, including its parameterization and how to estimate the parameters, as well as how to handle the case of multiple classes. So yeah, what is logistic regression? Okay, so we want to model the relationship between the probability of an outcome, P of X, and the features or some predictor X. So how can we do that? Well, when we looked at linear regression models, the output was modeled as a linear combination of the input features. So let's consider this one possible approach to the problem. The introduction to statistical learning text uses this different notation involving beta. So they have beta 0 and beta 1, whereas we would have B and weights W. But yeah, if we try to do that now, if we try to treat this like a linear regression problem, we're going to run into some problems. And yeah, and again, a good explanation of this is in the ISL text. And so in that text, the authors provide the example of predicting whether an applicant will default on a loan using their debt balance as a predictor. And so the data associated with this example is given in the scatter plot here. So the balance takes on the role of the x-axis and the outcome is indicated on the y-axis. And so each orange marker here represents one applicant, which are characterized uniquely by their balance in this case. And so the balance can take on values anywhere along this line from 0 to 2,500. And then the outcome is either zero or 1. They either defaulted or they did not. And so what we can see is that there's lots of applicants with balances up to around 1,200 that don't default. But after that, we start seeing quite a few applicants that do default. And so if we try to fit a linear model, we would actually see something like this blue line here, and it would give us negative probabilities for balances near 0. That's impossible. Probability can't be negative. And then if we were to extrapolate beyond the range of this chart, maybe at I don't know, balances of $10,000 or something, we would get probabilities greater than 1. So yeah, this model gives nonsense results because the output for a probability must always fall between 0 and 1, regardless of the value of the predictor, in this case, balance. Okay, so can we transform this linear combination into something that behaves like a probability? And so this is where the logistic function comes in. So the equation of the logistic function is shown here. And so how this works is we start with a linear combination of the input features, represented as the dot product between the feature vector and the parameter vector. And we raise Euler's number to the negative power of this linear predictor. And so yeah, to build some intuition here, when the linear combination is large and positive, the exponentiated term, this whole thing goes to 0. And so we're left with 1 over 1 for a 1 output. On the other hand, if the negative term is large and negative, then this term here will actually blow up, and this whole expression will be drawn close to 0. Yeah, and then if the linear combination is around 0, then e raised to 0 becomes 1, and so this whole expression will evaluate to about 1/2. Essentially, the probability of an outcome is a coin flip if the linear predictor is around 0, around 0. So applying the logistic function transforms the linear combination into a number that's constrained between 0 and 1. And this is exactly what we want to model probabilities. So logistic function is plotted in the figure on the right here. It's nonlinear, it's smooth, it's a monotonic transformation. Always outputs a value between 0 and 1, no matter what the input is. It's S-shaped, so it's also called the sigmoid function. And so we can also relate this back to the perceptron model, which we saw a few weeks ago, and I've shown here. And that is, we saw it's a linear classifier that also works in the binary classification setting. So the perceptron takes a linear combination of the input features. So that means we take the input features and then we weigh them by the parameters. We sum all those weighted features up. And then we apply a step function sign operation to produce a hard decision, either -1 or 1. We say that the perceptron is a discriminative classifier because it draws a linear boundary to separate the data. But it doesn't handle probabilities, only direct binary decisions based on the sign of the linear combination. And so the logistic regression model is similar in that both models rely on taking the inner product between the parameter vector and the feature vector, but their outputs differ. Um, Logistic regression applies a sigmoid function after computing the dot product. So this gives us something between 0 and 1 that we can interpret as a probability. For large absolute values of the dot product, both models will behave similarly. The perceptron will make a binary prediction, and the logistic regression will output something very close to either 0 or 1. However, when the dot product is near 0, the logistic model gives us more nuance. So it provides an output that reflects the uncertainty in the prediction. In this case, the perceptron will still make a hard classification. And so it's this ability of the model to model uncertainty that's the big difference between perceptron and logistic regression. So in the ISL text, the authors return to the probability of default given the credit balance example. So on the left here, I've got the linear regression solution, and on the right, we've got the learned logistic regression model. They use a slightly different formulation of the logistic function, but it can be shown to be equivalent to what we've been working with so far. And so now, instead of a straight line, we get that S-shaped curve. For very low balances, the predicted probability of default is pretty close to 0. And for very high balances, it approaches 1. In the middle, where balances are neither too low nor too high, the curve smoothly transitions. It gives us a continuous range of probabilities. And so this curve better reflects the real-world behavior of probabilities, gradually increasing as the balance increases without crossing the 0-1 boundary. And so I'd like to say a bit more about the significance of our choice of a monotonic function in that output layer. And so in certain industries, such as the lending industry that's highly regulated, it's important to have simple and interpretable models. For instance, when a credit application is denied, lenders must provide specific reasons for rejection. And so in this context, logistic regression makes sense because it's interpretable. Lenders can identify which variables contributed to a decision to accept or reject a loan applicant. And so monotonicity is a part of this picture of interpretability. And so what I mean by monotonic is, for example, a customer's debt increases, so should the probability of the outcome, as we see in blue. And so for a non-monotonic relationship is shown in green. We can see how if we had a model that did something like this, it could lead to confusion. For example, you might end up with a situation where Bob was granted a loan because he had a balance of $1,200, but then Joe was denied because he had a balance of $1,000. And so, yeah, okay, that might not be the best example, but yeah. So the model, even if we have a model that might fit the data better, the decisions couldn't be defended as easily. And so logistic regression offers a significant advantage because it's built on a linear combination of features. And so the relationship between the input variables and the probability of an outcome is always monotonic. And so this ensures that as a predictor, like balance increases, the probability of default either consistently increases or consistently decreases. So it makes the model easier to interpret and therefore justify. Okay, so we've talked about the problem. We have our hypothesis class, but how do we estimate the parameters? And so, yeah, it's now time to learn a specific function within the logistic hypothesis class that we've been talking about. Essentially, we want to find what those parameters W in our model should be. And so before we do that, let's take a step back and contemplate what this output means a bit more. So we said before that the logistic function allows us to model the probability that the label associated with a feature vector is 1. And so we we interpret the output of the function as the probability that an observation will be labeled positive for a particular feature vector associated with the sample. So within our setup, let's make this interpretation clear by equating the output of the learned model h of x with the conditional probability that the associated outcome is 1, given a particular feature vector x and the parameters of our logistic model w. So importantly, y, the output of the model, is now a random variable, denoted capital Y. It's not deterministic. So one thing we need in order to fit the parameters is a probabilistic model of the outcome or a label. Okay, so how can we go about modeling this probabilistic outcome? So one thing we know is that the outcome can take on only one of two values. It's either 0 or 1. It's a binary outcome. And last week, when we had the lecture on maximum likelihood estimation and entropy, we encountered the Bernoulli random variable. And this allows us to model these types of binary random variables. And so for a quick recap, Bernoulli random variable is parameterized by p, which can take on any value in the range of 0 to 1. So a single parameter fully specifies the probability mass function for the two possibilities of a binary random variable x, as the total probability must always sum to 1 if a random variable x takes on a value of 1 with probability p. It'll take on a value of 0 with a probability of 1 minus p. So this makes total sense in our cat adoption scenario, because if a cat has a 90% chance of getting adopted, there's a 10% chance that it won't. And so another thing is that whereas last week our random variable was x, now our random variable refers to the outcome y. But crucially, the Bernoulli parameter p is no longer fixed. So what we actually need this to change based on the cat's profile. It's a conditioned probability. So for example, if a very playful kitten arrived, we would expect a high probability of adoption, highly skewed probability mass function associated with the Bernoulli random variable. If on the other hand, we had a senior indifferent cat, we would expect the probability to be the PMF to be skewed in the other way. There's a chance it might get adopted, but overwhelmingly likely it won't. And so things in between those two examples were very, very uncertain of which way it's going to go. In these cases, the features do not strongly favor one outcome or another. So the Bernoulli random variable in this case models the conditional probabilities, as I said, capturing how the logistic regression frameworks adjusts based on the data we have about each cat. Okay, so now that we've got a probabilistic model for our outcome using the Bernoulli random variable, we can use maximum likelihood estimation to solve for the parameters given the data. So as we did for linear regression, let's start off by writing out the likelihood function. For the Bernoulli random variable, the likelihood function of its parameter p, given a set of n observations y, is given by this equation here, where I'm using bold y to denote the entire set of outcomes. And so assuming the outcomes are independent, the likelihood p given the data is the joint probability of independent outcomes in the data set. So we compute this by multiplying together their individual probabilities. The probability for any one data point is then what's inside this product operator, which is p raised to yi times 1 minus p raised to 1 minus yi. And so the motivation behind this particular structure is that yi in the exponent allows it to act like an indicator variable. So if yi were 1, then the probability would just reduce to p. And if yi were 0, then the probability would be 1 minus p. And so to simplify the product and make this expression easier to optimize, we can take the logarithm of the likelihood. So log likelihood, and this has the convenient property of turning the product operator into a summation operator. We can then expand the expression inside the sum by applying the property of logarithms that states that the log of a product is the sum of the logs of the factors. Okay, so we have the likelihood function for the Bernoulli random variable given a set of outcomes y. But what we're interested in is figuring out the parameters for the logistic function. Okay, so we have the likelihood function for the Bernoulli random variable given the set of outcomes y. But what we're interested in is figuring out the parameters for the logistic function. So that is, we need to reparameterize this likelihood function for our parameter vector w, given the data, which for us is the set of feature vectors x and the set of outcomes y. So how can we do that? Well, let's recall that in logistic regression, the output of the model represents the conditional probability of positive outcome given a feature vector in the parameters. So this probability for a specific feature vector is computed using the logistic function applied to the linear combination of the parameters and the features. Let's denote the output of our model associated with a particular feature vector xi as small p outside of xi and w. And then we can substitute this into the Bernoulli log likelihood to obtain a new log likelihood function that depends on the parameter vector. All right, so to build some intuition about what we have here, let's examine the case when the outcome is 1. In this case, the log likelihood simplifies because the term involving the complement of the probability drops out. So yeah, this whole term would drop out. And so this would leave us with a simpler expression that directly involves the probability itself. And so we can then apply this rule here to obtain this expression. Similarly, when the outcome is 0, we can do something, we can do another simplification, but it's going to give us a different answer. In the case that yi is 0, this other term is going to drop out. And we can arrive at this last expression, which involves the complement of the probability. And so yeah, this final expression here results from applying a whole bunch of logarithmic and algebraic manipulations, and I've included the full details at the end if you'd like to explore them further. But yeah, you can note a kind of mirroring between the case where yi is 1 and the case where yi is 0, specifically in the sign of the exponent on Euler's number. Okay, so continuing on, let's consider the case for the binary outcome. One where the outcome is 1 and the other where it's 0. And so each case leads to a slightly different form of the log likelihood, depending on whether the event occurred or not. So when the outcome is positive, the log likelihood involves the negative log of the exponent, raised to the negative power of the linear combination of the features and parameters. And when the outcome is 0, it involves the exponent raised to the positive power of the linear combination. So we can actually unify these cases by introducing a new variable, tilde yi. And so that's going to be 1 when y is 1 and -1 when y is 0. And so if we do that, we can rewrite the log likelihood in a single compact form. Now, regardless of the outcome, the log likelihood is expressed as a summation over all variables, over all observations. A single expression that applies to all data points. Okay, so we're now ready to formalize the objective of logistic regression, which is to estimate the parameter vector that best fits the data by maximizing the likelihood. And so this is equivalent to minimizing the negative log likelihood of the data. And so we can then express this as an average over all data points. We can actually discern the loss function. And so the actual loss function is called cross entropy loss. This is the loss function down here. We call this cross entropy loss. And so unlike linear regression, here the loss is a nonlinear function of the parameters. So this doesn't admit a closed form or analytical solution. So it can't be determined exactly in a finite number of operations. Instead, it has to be approximated using numerical techniques that we'll get to a bit later. Okay, so let's see if we can build some intuition for how the cross entropy loss function penalizes the model's predictions. Okay, so I have in this table here I have two cases: a row where the label is positive and a row where the label is negative, and then a column for when the inner product of W and X is very negative. And one where it's very positive. Okay, so if the true label is negative and the inner product between these two is much less than 0, that means that the model is confidently predicting the correct outcome. So then we have e raised to a negative times a negative times a negative. So we have e raised to a very large negative number, which is about 0. So the loss becomes the log of 1, which we know is 0. So we've made a very confident prediction, and we're correct about it. And so we don't suffer a penalization. On the other hand, if the label is positive but the inner product is negative, then there's a sign mismatch. And this is going to, the exponent term will actually dominate the loss. So in this case, the loss becomes proportional to the inner product. And so cross entropy loss not only penalizes incorrect predictions, but also penalizes overconfident wrong predictions. Okay, and so we could also conduct a similar analysis for the positive cases. But yeah, so let's see what this looks like in a figure. So what we have here is the linear predictor on the x-axis, the inner product between parameters and feature vectors, and then this cross entropy loss on the y-axis. And so for the negative class, shown in blue here, when there's strong disagreement between the predicted label and the actual label, the loss increases linearly with the inner product of the positive labels. So for example, if the actual label is negative and the output of the linear predictor is giving us something very large and positive, then there's going to be a huge loss, and we're linear with the size of the loss. Linear with the size of the prediction in this regime. And then on the other hand, if the actual label, if the true class label was positive and we're outputting a very negative number, then we're going to suffer a huge loss. But on the other hand, if we're outputting large positive number and the true class is positive, then there will be very, very low loss, close to zero loss. So yeah, the idea is that cross-entropy loss increases as the predicted probability diverges from the actual label. So a perfect classifier would see the loss approaching zero as the predicted probability aligns with the true label, and the penalty would be minimal. So yeah, the loss function penalizes incorrect predictions, but also ensures that the model doesn't become too overconfident in making predictions. So it leads to a more balanced and accurate model overall. Okay, so I mentioned that we can't analytically solve for the parameters that minimize cross-entropy loss. And so what we need to do instead is use something called numerical optimization methods. So two of these are gradient descent and stochastic gradient descent. So first, let's just recall quickly what the gradient of a differential function represents. So the gradient is a vector of the partial derivatives of the function with respect to its parameters. So it tells us the direction in which the function is increasing the fastest. In gradient descent, our goal is to move in the direction opposite to the gradient, as that's the direction in which the function decreases the fastest. The gradient descent is an iterative algorithm, so we start with an initial guess for the parameter vector, and then at each step, update the parameter vector by subtracting a fraction of the gradient at the current point, controlled by a step size parameter eta, which is this n shape thing here. So there's a few ways to select this step size, this eta parameter. Some option includes setting it to the largest singular value of the Hessian. You could also decay this with successive time steps or make it adapt to the magnitude of the gradient. So one drawback of gradient descent is that computing the gradient for the entire data set can be computationally demanding, especially when dealing with large data sets, as it requires calculating the gradient over all points at every single iteration. And so this is where our stochastic gradient descent comes in. And so instead of computing the gradient over the entire data set, SGD approximates the gradient by selecting a random subset of the data, and so a mini batch at each step. So the update is based on this smaller, randomly chosen batch rather than the full data set. And so while the gradient estimate at each step is noisy, the expected direction is still correct. And so the reason why this works is that the average of the gradient estimates over many iterations approximates the true gradient. And so this randomness makes SGD much more computationally efficient than full batch gradient descent, especially for large data sets. So in the plots on the right here, I've got the trajectory followed by gradient descent, starting from some random initialization associated with high loss in the outer contours, and we're trying to get to a minimum in the center. And so in full batch gradient descent, we can see smooth, steady progress towards that minimum. In the right, this is the path associated with SGD, stochastic gradient descent. So we see a more erratic path of gradient descent, but it does still find the minimum. So yeah, there's a trade-off between these two methods. Gradient descent is more stable and produces more accurate updates, but it can be slow and computationally expensive for large data sets. Stochastic gradient descent, on the other hand, is faster and computationally cheaper, but the updates are noisier and less stable. Despite this, we know that if the objective function is convex, stochastic gradient descent will still converge to the global optimum. It might just take a more erratic path to get there. So in practice, the choice between these two methods depends on the size of the data set and the computational resources available. For large data sets, stochastic gradient descent or a variant like mini batch gradient descent is often preferred because it offers faster convergence without requiring that full gradient at every step. Okay, so gradient descent and stochastic gradient descent are first order methods because they rely only on the first partial derivative. Newton's method, otherwise known as the Newton-Raphson method, uses information about the second derivative of the loss function. Newton's method is a general means of finding the roots of a function. So that is where the function intersects the horizontal axis. And it works by fitting successive tangents to a function at a particular valuation point. So for example, this pink point here, if we started there, we would fit a tangent at that point. We would find out where that tangent intersects the x-axis, and then evaluate the function at that new point, and then fit a new tangent, find out where that tangent intersects the x-axis, evaluate the function there, and so on and so forth. Newton's method can be very fast in terms of how many iterations it takes to get to the minimum. So we can converge to the optimal in fewer iterations, but it can be computationally demanding, and I'll get to that in a few minutes about why it's computationally demanding. But yeah, so first, how does Newton's method work? How does it know where the line will intersect the W axis? All right, so let's see if we can derive the update. So starting at W0, our immediate goal is to get to some W1, which is closer to the root of the function that intersects with the W axis as indicated by this red dot. So let's define delta 0 as the difference between these 2 points. And so that's W1 minus W1 is 0, and therefore W is W0 plus delta 0. So another thing we know is that the tangent at W0, the slope of this pink line here, is equal to the rise over the run of the function. So the rise in this case is the rise in this case is our goal ending height of 0, 0 less our starting height of W0. So yeah, rise over run, we're ending in 0, and the starting point was f of W0. And then the run is delta 0. So we can calculate the slope here, and then we can substitute this into our equation that we had first. So rearrange and solve for delta, and then plug this back into the first equation that we had. And so this gives us the update for to get to W1, but this generalizes to give us the parameter vector at time step t plus 1, given the parameter vector at time step t. Right, so I said it uses second order information, but so far we've only used the first derivative. But Newton's information finds the roots of a function, so that is where the function's 0. And so to minimize a loss function, we're interested in those points where the gradient of the loss is 0. And so we want to apply Newton's method to the gradient of the loss function. Right, and so that's going to give us second order information. It's going to require second order information in terms of the second partial derivative. And then to generalize this to functions of more than one variable. So for example, when we're dealing in functions in R to the D, which we have been doing most often, we generalize this to the inverse of the matrix of second partial derivatives of the loss function. So this is the inverse of the Hessian matrix times the gradient of the loss. Right. So yeah, the fact that so this requires inverting a matrix. So this is why Newton's method for finding the minimum of loss function can be more computationally expensive because we have to invert this matrix in order to compute the Newton update. All right, so yeah, so everything that we've been dealing with so far has concerned binary predictions. So binary logistic regression, applying probabilities to predictions of binary outcomes. But often we might be dealing with more than two possible outcomes, and we want to be able to maintain this probabilistic interpretation. So how can we handle classification when there's more than one class? And so, yeah, just to give, yeah, so we want to see how to handle binary logistic regression when we have more than two classes. So yeah, on the assignment, for example, you've been working with the iris data set that I've depicted in the middle here. So the data set contains three species of flowers. There's the setosa, the versicolor, and then the virginica. And then the scatter plot in the middle here, each point represents two features of a specific flower. Its sepal length in centimeters and its sepal width, by the position on the y-axis. And so our binary logistic regression model gave us a single probability, the probability that the sample belonged to that class. In the cat adoption scenario, this gave us information about the probability that the cat would be adopted. But here we need to select among three classes. So the binary classifier doesn't apply as it can only discriminate between two outcomes. So the strategy we can use to build a model, in this case, is known as multinomial regression. So this generalizes logistic regression for situations involving multiple classes. So instead of just one probability, multinomial regression returns multiple probabilities, actually giving us a discrete probability distribution over the classes. So for any particular flower or point on the scatter plot, the model would tell us the probability that it belongs to each of setosa, versicolor, or virginica. And so why is this useful? Well, in the scatter plot here, we can see that the purple points, those associated with the setosa class, this is easily distinguishable from the other two. In fact, the points are linearly separable from the other pieces. However, the points associated with virginica and versicolor are very strongly intermingled. So we might expect the model to be more confident for predictions in setosa than for either versicolor or virginica. Okay, so how can we do this? Well, let's take a look back at the architecture of our logistic regression model. In the binary model, we have our input features x1 through xd padded by 1, where we compute a linear combination of the weights and biases, and then finally apply the sigmoid function to turn that into something representative of a probability. And so we want an architecture that will work for multiple classes. So we want to do some kind of copying of that basic architecture from the binary case. So to fit this all on one slide, I'm gonna shrink down the classifier a bit and rotate it so I can give ourselves some space for whatever that ends up looking like. So I've rotated the architecture, so now we have the features of the data coming in from the top, and the information flows downward through a weighted sum, and then the sigmoid operation to give us the final modeled probability. So yeah, if we were interested in the probability that a sample belonged to versicolor color only, this architecture would allow us to answer that question. But yeah, like I said, one way to proceed would be to give each class K its own set of weights and a bias, and then its own summation node, and then apply the sigmoid function as we did before. But yeah, there's a probability. There's a problem with this architecture. So let's suppose we're interested in the probability that a new sample, potentially this flower at the top, belongs to the versicolor class. So I've denoted this as k equals 2 in the middle. It's totally possible that the final output we get is just not inconsistent with the rules of probability. So the classifier might predict that it belongs to Setosa with 33% probability, Versicolor with 90% probability, and Virginica with 57% probability. So these can't all be true because the total probability is greater than 100%. Yeah, this architecture isn't quite right yet. Okay, so the way around this is to use the information about what the predictions are about the other classes uh, in the prediction for a given class. So that is, we have to have some kind of normalization across this final output layer. And so the way this is done in multinomial regression is through the softmax function, which is given in this equation here. And so what this says is that the probability that a label will take on a value k, where k indexes over the number of classes, given the feature vector and the weights in the model, is given by exponentiating the linear combination for that particular class k, divided by the sum over all such exponentiated linear combinations associated with each of the C classes. Okay, so yeah, now if we were to examine the intermediate values in our model, we might see that the summation nodes output a set of values on the real number line, uh, something like this. But then after passing this through the softmax function, we get new values. The total probability here sums up to 100%. 5 and 77 is 82 plus 18 is 100. And so the largest output is associated with the largest probability, and the smallest output gives us the smallest probability. So this aligns with our intuition. Okay, so that brings us to the end of this lecture. So yeah, just to sum up what it is that we talked about today. Yeah, we talked about logistic regression. We talked about specific real-world scenarios in which this makes sense as an alternative to linear regression, as an alternative to binary classification and linear regression. We also talked about the specific hypothesis class, specifically the logistic function. Talked about conditional probability, the sigmoid function, and its effect on the linear predictor. We also saw this very deep connection, or this fundamental connection to the perceptron structure. So because the logistic regression function has this relationship, we can use all of that knowledge to be able to sketch out rough decision boundaries given a particular probability threshold. We also went over the cross entropy loss. So we saw how it behaves when the model output disagrees with the actual label, and then what it does when there is agreement, and then confident agreement as well. Finally, we saw how to generalize this to the multi-class setting in multinomial regression, taking advantage of that softmax function to normalize across the output layers for each of the classes. And yeah, we encountered 3 algorithms for iterative optimization, specifically gradient descent, stochastic gradient descent, and the Newton-Raphson method. All right. So that concludes this talk. We'll see you back here for lecture 6, where we're going to start talking about support vector machines. All right, see you then.